Hello everyone. Now today I will be sharing the concept of primes. Now suppose an integer. Let's suppose the integer to be p. Okay. Now p is an integer, so it belongs to capital Z. Now this is the symbol for integer. So now p is said to be a prime if it is only divisible by 1 and the number itself, p. Right. Now this is the standard definition of a number being prime, which is a number is said to be a prime if it is divisible by 1 and the number itself. Right. But suppose, what about -1 and minus p? So -1 is also like a part of a factor of p, right? So -1 should also we need to consider. So the definition would be more clearer if we take the only divisors are plus minus 1 and plus minus p. Okay, moving on. Now what's a canonical form of an integer? I will write the spelling for you. Canonical form. Now canonical form of an integer. So what is canonical? It's basically the sequence of digits, okay, which doesn't start with 0. Okay, now canonical form of an integer, suppose I'm taking an example, but firstly canonical form of an integer and canonical decomposition are basically the same thing. And if you're a CS student, you would probably know what is canonical in your languages. Now canonical decomposition of suppose 12. Now 12, so canonical form of an integer can be expressed as a product of primes. Okay, now what is the product of primes for 12? 2 squared and 3 to the power 1, right? So this is the canonical form of an integer for 12. Now this is the basic canonical form or the decomposition. Now let's move on. Now the fundamental theorem, let's study the fundamental of arithmetic. Now what is the fundamental theorem of arithmetic? So it basically says that if there is a number, or let's say the number is an integer. Okay, so there is an integer which is greater than 1. Okay, the number of the integer should be greater than 1. Suppose n is an integer. Wait, n is an integer. Okay, so it is greater than 1. So yeah, the fundamental theorem of arithmetic says then if n is an integer, so n should be either a prime or a product of primes. Product of primes, Obviously I will be showing you a couple of examples how. Now see, let's take a number. Suppose I'm taking three numbers, 7, 7, wait, 12, 89, and suppose 55. Now which are primes, you first find out. So this one is a prime and this one is a prime, right? Because 7 doesn't have any divisor except plus minus 1 and plus minus 7. Also for same goes for 89. So why I'm telling it, because 89 is neither divisible by uh, 3 or 2 or anything like that primes. Okay. So we will know lot about the divisibility of primes in later of the video. Now what about 12 and 55? Let's see. So 12, I've discussed earlier, can be written as 2 squared, wait, and 3. Now 2 is a prime number, also the 3. So you're seeing it that it can be written in the product of primes. Now you can obviously write it in this way, that 2 multiplied with 3 multiplied with 2. This can also be written, write it in the canonical form, since we know now what is canonical one. So 55, how can we write? So 5 times 11, that is the thing. So 5 times 11 is 55, and 5 is a prime, 11 is a prime. Okay, so suppose the number p that we are considering in the first one is a product of two integers, suppose a and b. Okay, a and b. Now a is a separate integer. Now I've shown you that it can be written as the product of integers or the integer itself. We are supposing it to be the product of integers, so it can be written as p1 to the power alpha 1 comma p2 to the power alpha 2 dot 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 pn alpha n. Now we do not know how many primes or what is the degree of the prime. Okay, now b can be written as, suppose, q1 alpha 1 q2 alpha 2 dot 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 qn. Oh sorry, the powers have made the same thing. Wait, beta 1 beta 2 and beta n. Okay, now you would be probably confused with the alpha 1 alpha 2. There can be also like possibility that p1 alpha 1 multiplied with another integer, and it could have several primes. So in that way it will go on, and at last and at last it will be like this form only, p1 alpha 1 p2 alpha 2 dot dot pn alpha n, pn to the power alpha n. Now we have shown that a and b will be the product of primes. We do not know the degree of a, p1 p2 or any primes. So p1 actually here, pi I would suppose, and qi are primes which are necessarily to be written, because a reader doesn't know what is the, like, where it is prime or not. Okay, now moving on. So p, the number p, which is the product of a and b, can be written now p1, wait, yeah, p1 alpha 1 p2 alpha p2, wait, p2 alpha 2 dot 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 pn alpha n, q1 beta 1 q2 beta 2 dot 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 qn beta n. Now from this you can make yourself clear that any number, if you take, it can be written as the product of primes if the number p is greater than 1, obviously. Okay, so let's move on. And another thing, if a number p is not divisible by either one, sorry, if the number p is divisible by any number except plus minus 1 and plus minus p, then it is said to be a composite number. If p is like p has divisors except plus minus 1 and plus minus p, then it is composite. Not for this one, okay, not for the above one. Now let's learn another important topic, which is sieve of Eratosthenes. Now the name is actually a big one, a bulky one, which is you are supposingly it to be very tough. I will try to give my best to make you understand what is the thing all about. So basically, before, like when the primes are like firstly made, like these are the prime numbers, so then at that time till now also, the number, if we want to check if, like, a, suppose, to be a prime or not, then we need to check with all the prime divisors from 1 up till a, right? Now this is a like heavy job for everyone to check. So Sieve of Eratosthenes have made easier, a better way to like check it is a prime or not, or like a better way to say is that, like this method can be used by anyone to find the non-trivial divisors. Wait, divisors of any prime or a prime number. Now, what is a non-trivial divisor? So what is a trivial divisor? Then we can understand what is a non-trivial one mean. So trivial divisors mean plus minus 1 and the number itself. So these are the the trivial divisors of any prime. So I'm considering a to be a prime. Okay, now if a is a prime number, then it should have only the trivial divisors plus minus 1 and plus minus a. But suppose we do not know whether it is a prime or not, so then it could have some non-trivial divisors. Okay, so non-trivial divisors means the divisors which are except 1, like plus minus 1 and plus minus a. So it's in the between. Okay, so it's between 1 and a. So this is an interval sign, this is a open interval. Like I shouldn't have used this because it considers all the real numbers too, but we will not be considering any real numbers. Okay, I'm just showing you that it will range from 1 to a, the all the integers part. Okay, so better I shouldn't write that. Now the thing, so let's learn what is the thing by examples. Suppose 2093, great number, right? 2093. So what are the prime factors or the divisors of 2093? I mean the divisors. So the prime divisors, if we need to find out, is a hectic job, right? Now let's learn it in a easier way. Okay, so root over 2093, if you see, root over of 2093, it's not a perfect squared, right? So if you find the root over of something to be ranging from, like, so the 2093 will range from 46 and 45 if you find. Now, so we need to check, like write all the primes from 1, sorry, from 2, 3, 5 dot 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 up till wait, up till 46. Okay, now that I was saying, so you need to see all the divisors, all the primes from starting from the first prime, which is 2, and up till 46. Okay, so you will see that not is for up till 46. So up till 46, 43 is a prime. Okay, 43 is the last prime. Now if you see that what is the like the first prime which is divisible by 2093. Okay, so if you see, 2093 is actually divisible by 7. Oh, I'm sorry. Yeah, it's okay only. So 2093 is divisible by the first prime, which is 7. How? Means 7 times some number x will give you 2093. Okay. Now, so what is the number? What is the x number? It is 299. Okay, 299 times 7 will give you 2093. Okay, let's highlight this number. Okay, so now 299 is a new number, right? So if we find the square root, it is obviously again not a perfect square, right? So if it was a perfect square, I'm telling, so suppose some x number, it has a perfect square, suppose 16. So you will find all the prime divisors up till 16, so means it's below 16. Okay, since it's not a perfect square, we need to find the between per primes. Okay, so it will range from 18 and 17. Okay, now all the primes again starting from the first till 18. So it's starting from 2 3 dot 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 up till uh, suppose 17, 13 and 17. Okay, now see the first prime again divisor of 299. Okay, the first prime divisor of 299 is 13. Great. Now what is 13 times some number x will obviously give 299. So what is the number x? It is 23. Again highlight this one. And is there any prime divisor of 23, do you think? Obviously not, right? Because prime is the least prime means it's the least prime. Okay, so if you do the square root of 23 again, you will find not any divisors for that one. So we'll highlight 13 again. Now if you see 13, 23, and so I've highlighted this one, right? So I should have done 7 only, not 30. So 299 was not to be highlighted actually. Now so actually we have got our answer. So 293 has 3 prime divisors: 7, 13 and 23. So if you find the product, it will result in 2093. So 2093, the prime divisors is this one, not the factors. Factors is a different thing. So prime divisors means if we find the product of these primes, it will result in 2093. Okay, so does it end over here? Is this the sieve of Eratosthenes? No, this is not the this is the like previous knowledge of sieve of Eratosthenes. This is not the actual part. The actual part, which is done by Eratosthenes of Cyrene, I'm writing Cyrene. So Cyrene, Eratosthenes of Cyrene, what he has done is he was a clever person. Okay, after knowing all this new concept, okay, after knowing this new concept, he performed, like he developed a clever way of telling the non-trivial divisors of a prime or a number. So say, okay, suppose we take all the, like we need to find all the non-trivial divisors or supposedly all the prime divisors of 100, not 100. So we need to find, suppose we need to find all the primes of all the primes less than 100. Okay, this is the actual part, all the primes less than 100. So if you start now, you would probably end after 1 hour finding all the primes, but he found a way to do it a better, like much more quicker than the finding all by yourself. Okay, first prime is 2. Wait, so we'll start from 2, 3, 4 dot 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 up till 100. Okay, so these are all the numbers starting from 2. We will start from 2, like I'm taking an example obviously, so we will start from 2 only, not from 1. We could have start from 1, is no problem, but the primes start from 2, that's why we are taking that example. Now, so the primes, so first number is 2, the 2 is a prime number, right? But the multiples of 2, the multiples of 2 can never be prime. So first the multiples of 2 can be eliminated. So I'm not writing the full spelling, eliminated. So the multiples of 2 can be eliminated. Then what we can do is multiples. Okay, now when we are removing the multiples of 2, we should take the thing in that mind, will not eliminate 2 because it's already a prime number. So the first one is 2 and we will keep 2 and eliminate all the rest of the multiples of higher multiples of 2. Now we will eliminate the multiples of 3. Why? Because the next prime or the next number is 3. Now next number is 4, which is the multiple of 2, so we'll not consider that one. So multiples can be eliminated. Number 3, so 4, then 5, next number is 5. So 5 doesn't come under 2 multiple or the multiple of 3, so now we will eliminate the multiple of 5. Eliminated. Now if you see the next prime, it is 7. So 7 doesn't also fall under 2 multiple, 3 multiple or 5. So now let's eliminate the multiples of 7. Eliminated. Now so till how much we will go, that is the main like question of ourselves right now, right? 100. Now what I said to you earlier, that root over of 100 will give 10. So we need to check all the primes till 10 in order to see all the prime divisors of 100. Not only that, but all the primes starting from 1 to 100. Okay, so for the prime divisors we will consider the primes from 1 to 10 for 100. Okay, so in that the last prime was 7, so the next prime, there is no next prime actually. Less than 10, there is no prime, so the multiples of 2, like the higher multiples of 2, 3, 5 and 7 are eliminated. All the remainings are only the primes less than 100, if you see, because we have eliminated all the prime divisors multiple. If you see, all the prime divisors, I'll write for you, prime divisors higher multiple. All the prime divisors higher multiple we have eliminated, so what is remaining are the only primes starting from 2 till dot dot dot, suppose 23 dot 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 89 and suppose 97, I guess this is the last prime. So this is actually the sieve of Eratosthenes. So this is the last concept of our today's video, the sieve of Eratosthenes. Now if you have doubts regarding this, you can ask in my comment section. So next day we will be starting with the next concepts of prime. Supposedly we will do Goldbach, conjecture, Goldbach conjecture we will be doing in the next video, and I think some concepts are left from primes which we will be doing in the next class. And also, if I made some error, if you find out from this video, you can obviously comment down. I will rectify it. I'll see your comments. Thank you for seeing the video.